Good morning. Welcome to Krishna's class. Let us explore in this talk how the concept of labor pressure appeared. Now, this came while modifying the concept of Riemann integration. Recall that Riemann integration did not meet our objective in the sense that all Riemann integrable functions on an interval AB, a bounded interval, which we designated by Riemann integral AB. AB is a bounded interval. Bounded interval. It's not complete. In fact, we constructed a normed linear space from RAB with the L1 norm. L1 norm was this, that is the norm that we have used was whatever. Now, it has found that it's a semi-normed linear space because this did not happen to be a norm on RAB. In fact, it became a semi-norm. It simply failed to meet the requirement that norm of f equal to 0 this did not was not true for elements in RAB. Then of course what we did was we constructed an equivalence class of functions R tilde AB on which again was defined as the norm, and it so happened that once you consider this as the equivalence class of elements, that is f related to G if integral mod f minus G equal to 0, then this became a linear space, a linear space, because you could actually extend the addition and scalar multiplication and then could make it a linear space. Further, we could also define a norm on this. In fact, the norm defined in this way, or the length function defined in this way, turned out to be a norm. Because in this class, we said f equal to 0, identically equal to 0, or rather we said f is equal to 0 whenever f is related to 0 function. That is the criteria. With that, it became corrected. So R tilde became a normed linear space, and then we proved that is not complete. By which we mean Cauchy sequences in R tilde did not converge to an element in R. Now this made it difficult to do analysis on the Riemann integrable functions comfortably, because you see that to choose Cauchy sequences and then go for their limits, may not find a limit. Therefore, further analysis on this space was not possible. Okay. So that is a sort of shortcoming that we observed with RAB. Therefore, the question is how to situation. Obviously, you see that you have RAB. Riemann integral functions with its norm is not complete. Therefore, see, it has a completion. This is actually the completion of R. It's laughter. That means we have to put in more elements into it so that the limits of all Cauchy sequences would find a limit in this class. Okay, and that too something that's optimal. You don't need it in details. So how to get this done? Now this was the. So we have to seek an extension. But how do we do this? This is the question that. Okay. Because one could characterize the Riemann integrable functions, etc. Because we found that we are only talking about bounded. So the sort of restrictions that we had was AB is a bounded interval in R. Secondly, if and only if the set of discontinuities F is bounded on AB and the set of discontinuities F R have lengths. This is exactly concept of measure later. This is what we have. What a nice character. When we found that we do not have adequately many elements in this class to assure completeness. That was the problem. So how to pick new elements from this? This is the problem. So what do? We get back to the drawing board. So let us briefly recall what we did in the case of Riemann integral. See, in the case of Riemann integral, suppose this is the interval AB and the graph of the function you can even work with a non-negative function. Yeah? Take negative one. So, now how did we find the integral of this? Recall, we first observed that we were not worried about the classical notion of differentiability or classical notion of integral as antiderivative, but we computed the area enclosed between the ordinates, the function, graph of the function, and the x-axis. So this area was something that we had been worried about. Computed. Our strategy there, I think it is worth recalling. Our strategy there was to subdivide the domain into or partition the domain into zones. So we had the partition P. X0 so the partition that made use of. And then based on this partition, we approximated this function by what is called a step function. So approximation of above and below by step functions. Whose area the area related to sum of the finite areas of rectangles. Okay, let us see how it comes up. Now you see, you have this one, this one, this one, this one, this one, this one. So what we did was we approximated from below by a function a step function below that, and then okay. So look at this function. This function is a step function, okay, which takes certain values on certain constant values on the intervals x0 to x1, x1 to x2, x2 to x3, etc. Now there is also a, and this function is stays below, the graph of this function stays below the graph of the given function. This is why it, now what is the what is the upper approximation? Upper approximation was done by another step function. The step function has the graph, yes, and this here, and so on, and eventually this one. So this is the approximation, right? So you have two areas. One, of course, this one. This is the so you see the area marked here is something less than the area that we are. Okay. On the other hand, you have the upper approximation. Upper approximation. You have these areas. comes up to this, and then you have the upper approximation here, then again upper approximation here, and again the upper approximation here. So you see you have two types of areas. One and you have the upper approximation given by so you see that the lower approximation is less than or equal to which we designated by maybe a bit of repetition, but unfortunately it is better once you get these ideas fixed. You will see how these ideas have evolved. So I don't think I would hesitate to repeat it. Okay. So you see that the lower approximation we designated by, suppose this is the partition. Suppose the partition we had this inequality area what I can color code it and write this L is less than or equal. The upper approximation subordinate the partition P. Now what one does is refine this partition. Okay. And then of course it is all clear. I don't want to repeat it. You take LF which is equal to supremum of P belonging to the class of all partitions of LP. And you know that this is less than or equal to the infimum of over all partitions or I would put this is what you get area less than or equal to infimum of overall P belonging to partitions of Q, P, F, which we designate by Qf. So what happens is that when you refine the partition, in fact what you can say is that the collection of all LPF, see, have this. This is the collection of all partitions is bounded above. By one of these upper integral. And so also is bounded below. Above by an upper sum any upper sum by any so these are always bounded. So therefore the supremum x is here, the infimum x is here. This we designated by LPF and so you have this what you call LF and you have this UF so this is the crucial observation. Now we said f is Riemann integrable. So we said f is Riemann integrable. If and only if they may not be equal. I mean, if they are equal, then you say that function is Riemann. Well, this was the definition of this. This is how we arrived at Riemann integral functions. So that collection we designated by Ra. Okay. What we have found is that this collection of functions is not large enough. Okay. Therefore, we had to go for a modification. Okay. Actually taking the whole problem to the drawing board again, trying to rework the integration altogether in a new way. How we could do this? Now this is the question. So let me take this out because I want to retain this picture. Okay. I want to retain that diagram and just take this out. So this will be my working space now until something which we want to compare with that occupies this. Okay. How to rework this? We'll make some small exercise. Okay. Once again, we take a function. This graph is something like this. Recall still stick to bounded functions, possibly. Okay. Rather, I think I would make a flattened picture so that whatever we do will be more visible. Okay. So let me rework. This is the important step. That's why I don't want to just run over it. You should understand how ideas. Let me just taking a continuous function for convenience. Need not be a continuous function like the one I have done. Okay. So what I have is again reworking this area. This is the area that I have to work. So this is y is equal to, this is the x-axis, this is the y-axis. How do I take up another approximation of this? Let me see. Now, here I had partitioned the domain. And I partitioned this domain with absolutely no reference to the given function. It had nothing to do with the function. I went with a partition, refined it. I went on to consider all the partitions into intervals, and then for each one you compute for the given function this upper integral, lower integral, and check whether they are equal. Okay, this was the strategy. But now we get approximations for the same in a totally different way. What we do is we now subdivide the range into intervals. This is the new strategy. In that case, what you do? So you take an interval, a typical interval. Okay, take a typical interval. Something like this. Look at the pullback of this. Pullback of this interval in the range in the domain. That means the set of all points in the domain which gets mapped into this particular interval. Okay. So you see that it is actually this. Suppose this interval is, say, something like CD. Then you see that this set that I mark. What is this? This is this set. This is what I take as F inverse of CD. Okay. Now you observe that, at least in the case that we have looked at, F inverse of CD, this is not an interval. This is not an interval. That is one problem. So what do we mean by the length of it? Okay, how do we use it? Suppose we can do something with that. Say, you can find something like length. Then you see that you have two approximations. The two approximations are one a lower approximation, the other one an upper approximation, because we are once again considering boundary functions. Okay, the lower approximation we use the same sort of coding, color coding, the same approximation. To see that the lower approximation to this is the lower approximation, and the upper approximation is this is the upper approximation. I'll use different color. So this is the upper approximation. So each arc of the curve in F inverse of CD can be approximated by the constant function C and D. Okay, so you see that you have the lower approximation. The lower approximation is on F inverse of f of x is C and the upper approximation to so they are constant approximations. Now let us compute the corresponding area. So the corresponding area is, so what is the approximation to this area? So Fx, see the area enclosed over here. So this is the area that we are calculating. Okay. So the area in F inverse of CD of the ordinates x-axis and f of x is approximated from below by what? C into C times length of F inverse of CD, and from above by D into length of F inverse of CD. Set CL of is the length of which we don't know because it's not an interval. It's not an interval. So this is an open question. So how do we construct? How do we? So this is the central problem that we encounter in this strategy. Suppose we have overcome this problem. Okay. Then what you can do is you can introduce a partition of the range. Okay. And then compute this kind of sums for each of the intervals that you have on the range. Then add up. You will get an upper approximation and a lower approximation. So you take all the lower approximations and add them. Take all the upper approximations and add them corresponding to each one of these intervals in the y-axis. You get what is called a lower area and an upper area. Okay. So the area will be, okay. So suppose we could overcome this problem. Then we get a lower approximation and an upper approximation the area enclosed between the ordinates x equal to b and the x-axis and the graph of the function. Okay. So you get a lower approximation and an upper approximation. Now we vary the partitions on the y-axis. Corresponding to each such partition, you will get a lower approximation and an upper approximation. Okay, we will do the details of this later. So corresponding to each partition we will obtain a lower approximation and an upper approximation. Essentially, what you are doing the same thing as you did here. Essentially, for each partition of the range we obtain a step function associated which stays F and another step function giving a lower approximation. Area. So also it gives another step function whose graph stays about F and giving its area, the corresponding area complete computed a upper approximation. This is the strategy. Okay, it's exactly as in the case of Riemann integral, except that in the case of Riemann integration, we partitioned the domain into intervals and then approximated the function by a lower step function and an upper step. Here we partition this by a the range into intervals and then get a lower approximation as a step function and an upper approximation as a step function. Now let me just compute this, show what it is. Okay. How do this function look? This is the approximation that we are doing. See, this is the approximation corresponding to the partition of this is the lower approximation, and then you have okay. So what is the approximation? What is the lower approximation, upper approximation, and the lower approximation that we get? Okay, the upper approximation is this one. Then on this part it is this one, this part, and this one, and on this part it's going to be this one, and on this part is going to be this, and on this part it's going to be this, and on this part it's going to be this. This is the function. Okay. So I just write it as a step function. Vertical lines are only indicated. Although in this case you get intervals, that is because the way in which we have chosen a continuous function. Otherwise, you may get even a very weird function. Okay. So what is the lower approximation? The lower approximation is this, this part, and this part. This is the lower approximation. So this is the upper approximation. This is lower. So you have the upper approximation and the lower approximation. For term like exactly like this. They are of course well regulated with the domain as this. Now you see that the uh, the F inverse of CD need not be an interval anymore. And that is the problem that we encounter. So you have to now devise the concept of length for sets, subsets which are not possibly intervals. That is one problem there. Secondly, such a length that you define turns out to be the same as the length of an interval whenever the set happens to be an interval. So that is important. So so our task. Then of course it's the same strategy. You compute an upper integral, you compute a lower integral. Now go for all sorts of partitions of the range corresponding to each one. You will be computing an upper integral and a lower integral. And then you see that the lower integrals are all bounded above and upper integrals are all bounded below. Therefore, to see that once again the supremum and infimum exist. Supremum of the lower integrals exists and infimum of the upper integrals exist. Okay? Right? And if these are equal, okay, the supremum of the lower sums and the infimum of the upper sums exist, then and are equal, then you see the function is integrable in the new sets. Okay, so that's the strategy, right? Observe that the that approximate from above and from below are functions of the time of the type sigma vi to here. Okay. Whose integral and the corresponding area approximately area and the corresponding approximating area is in fact sigma EI into length of EI. Now EIs are not necessarily. Now you can see that for the Dirichlet function, so Q for x belonging to these EIs to intersection or to complement 0, 1. I mean, these are the rational numbers and these are the irrational numbers. Therefore, they are no more intervals. Now you see this function, the Dirichlet function, is not Riemann. And would this also be not Riemann integrable? I mean, this is the question that you come. Now we want to resolve this. Therefore, here the problem is that you will have to attribute a length for to complement intersection. That means the set of all rationals on the interval 0, 1 and the set of all irrationals on the interval 0, 1, and we will have to define what is called length for these sets. They are no more intervals. Now that is a problem. So if this function is to be accommodated in the new scenario, then you would have to require these kind of things and then investigate once again the same way the lower approximation and the upper approximations to make coincide or not. Now you see, let us briefly recall what was the problem in the Riemann integral. The Riemann integral, this function was not Riemann integrable because every interval had a rational number and a irrational number. Therefore, your function took the value both 0 and 1 in this interval. Therefore, the supremum of the function on any interval was 1 and the infimum was 0. Therefore, the lower integral and the lower sum and upper sum, and so also the lower integral and the upper integral never became equal. But here you can see whether there is a way in which you can get over this. Okay. Now once again you are getting all the rational numbers here. So here the sets that you get, so you call this even. If you call this even, so you let us designate by even let even be defined then the step function that we are approximating is 1 into the characteristic function. Okay. So this is going to be the approximation. So you have 0, 1 split into therefore this is the upper approximation as well as the lower approximation that you get, and you can say that the integral of or the what you call the area of is always equal to 1 into length of E1 plus 0 into length of E2. And length of E1 is, suppose length of E1 is equal to equal to 1. Then of course you see that E1 union E2 is the whole interval and the total length criteria etc. will be satisfied. Then we see that 0. For any partition of the range, you see that this sum is going to be 0. Okay. Of course, the other approximation that you have are so you have the upper bounds, your lower bounds, and for this function. So there are only 4 types of sets that comes into this approximation, namely a function which is see, you have a different type of sets that you encounter are one, of course, the identically one function, and the other one was identically 0 function. The other function that you have are a function which is equal to 1 on, or there are only 3 functions. This is the one. Okay. These are the only step functions involved in the whole show. Okay. Therefore, you see that the area that you compute is always 0, and therefore you say that for both the upper approximation and for the lower approximation, you get the areas computed to 0. Therefore, the integral of this function is equal to 0. Suppose we modify this function, and suppose we modify this function into gx. Look at this function. The characteristic function of then the approximating functions are, you have Sx equal to 0 into the characteristic function of E1 plus 1 into characteristic function of, where E1, E2 are as above. Okay, where E1 is this and E2 is this. Okay, then you see that the length of equal to 1. Therefore, the integral of 20. So for G, both the upper approximation and the lower approximation are given by these functions. Collections involve this. Therefore, if you take the supremum, infimum, etc., this is what you end up with. Therefore, the integral of this G turns out to be 1, whereas the integral of f turns out to be 0. So in that case, you see, you are able to pursue the same arguments to compute the area by using approximating by step functions. Now, this is not possible in okay. Therefore, you see that this strategy did not work for this. This was one form. Okay, so let us now formalize all this. Therefore, what are the formulas? So let me just list out them. So the problems that we encounter are essentially or rather I would say the challenges that we encounter. Defining a concept of length for a large class of functions sets, large class of sets which are not necessarily intervals. Say another subsets. 2 for intervals such a length function identical with its length. So essentially you have to generalize the concept of length from intervals to a larger class of functions. How do we do this? This is the problem. Okay. So we would like the third one. If it is possible, to define a concept of length for every subset of I am not claiming that this is possible. So this is the condition, if it is possible. If not, for as large class of subsets as possible. But how do we do this? We'll make an attempt. Which includes terms. How do we do this? So let us take Remember, we need this to the concept to coincide with length for intervals. How do we do this? So through lengths we have to, through intervals we will have to approach. Okay. What we do is, so let E be a arbitrary subset. We enclose this in a countable collection of open intervals. This is possible. So we write E as you can even do it with disjoint open intervals. That need not. Now, what you do is we define the length of defined as what you call infimum of sum of I. This may be finite or infinite. Okay, but we are going for the infimum. Okay, for all such enclosures. Okay. There is another way of approaching this. Okay, let us do this. This may be finite or however, if E is contained in an interval I, which is bounded then it's going to be less than or equal. This is okay, right? So this is the outcome length. In fact, you can show that then length of E equal to here we are using properties like when you have two intervals which are disjoint, then you are actually adding up lengths of this. So this is something that you get. So probably this strategy is probably something that we can think of. Now the question that this is a very sophisticated question that you are asking. At the outset, we feel that we can do it for everyone. Okay, we need some further properties. So that is some way of getting what is called a concept of length. Does this length function behave possess or does it possess the properties of space? Is it possible to assert that or more generally, these are some of the desirable properties. Whenever disjoint collection, that is I intersection J is T more I equal to This is one problem. Uh, In any case, we can say this. As long as P is contained in M,